So this is problem 2.25, and it's kind of like 3 problems in one. It wants us to find the potential at distance z above all these different charge distributions. It also wants us to calculate the E field, but I'm only going to do that for part A. You could do it for B and C, but it's kind of redundant. So before, when we were finding the potentials, we were using Gauss's law and using the fact that E is equal to negative the integral of your E field. I would only do this way if you can use Gauss's law to find the E field, or if you can just find the E field quickly somehow, which basically means can you use Gauss's law to find the E field. If that's not a possibility, then we could use the definition of potential to find it. It's kind of a creative way to do it if you happen to have your E field, but when we don't have that, we can use this equation, which is V. Your potential is 1 over 4 pi epsilon naught. And then we'll do a sum from I equals 1 to n of q sub I over script sub ri. Now, this will actually turn into an infinite sum if you have a continuous charge density. So for B and C, it'll turn into an integral. But for part A, for example, we only have 2 charges, so we can actually use a summation to solve it. So for part 1, hopefully we can see these are both script R. We'll call this script R1 and script R2. And they're both equal to the same value, which if this is Z, and that's D over 2, then that hypotenuse, this is just a right triangle. So we can do right triangle trig to see that's going to be D squared over 4 plus Z squared square root in both cases. And your charge are equal, so that's also pretty helpful. So then we could just add the 2 charges. They'll both have the same denominator, which is that. So basically, I'll write it out explicitly first. And then obviously that's just going to be 2q over that bottom part. And I'm going to use, just write it the square root as an exponent, because for part A at least, I'll go ahead and find the E field. But I'm not really trying to practice derivatives. I feel good with that, just like I'm not going to overwork the integrals. I don't think that's really too useful. But we'll use the fact that your E field is the negative gradient of your potential. Now in this case, your gradient, well, the only part that'll survive is the d by dz, because that's the only variable that we have here. So I'm going to actually factor out all the constants, the 2q over 4 pi epsilon naught. We want to do d by dz, and I'm going to bring my exponent up by changing the sign. So this is just a power rule. If you do that, you have to add 1 here to get 1/2, which you'll be dividing by. And then you can do the derivative of the inside, which will be just 2z, and then you keep the inside. So long story short, you get your E field is equal to minus 2q over 4 pi epsilon naught times z over d squared over 4 plus z squared to the 3/2. Unless the problem wants the E field after it wants the potential, then that's not really overly helpful. I mean, it's a good way to check, but you could find the E field like we did before as well. Now, if they wanted both the E field and the potential, let's say the question had two parts, maybe it's a little bit quicker to find the potential first and then do the derivative, or you also could have found the E field and then did your integral. Doesn't really matter, but I'm not going to do that for part B and C. I'm not going to find the E field, but if you needed to, you just take the gradient of the negative gradient of your potential. And if you actually check, this is the E field you get in that example. For part B, like I said, this is a continuous charge distribution. All right, we have that little line segment here. So this is a continuous charge distribution. So that integral becomes an infinite, that sum becomes an infinite sum, which is just an integral. I'll just say from A to B for now. We'll work out the limits soon. dq over script r. Now dq is equal to lambda dx. Lambda is charge per length, so lambda times dx will just give you the charge. If you wanted to, you could find script r doing essentially the same way before. You have your z here, and we'll call it some point x. The other way you can do it is a little more systematically if it's not as clear. You can do vector r is the position from the origin to the point that we're actually calculating the potential, which is at a point z, so zk hat. R prime is the origin to some point of our charge distribution, which is along the x direction. And then script r, the vector, is r minus r prime, which is minus x I hat plus ck hat. And then in this case, we actually don't want the vector r, we just want the magnitude of it, which will get you x squared plus z squared square root. That's one way to do it. You also could have looked at it and just said, well, this is a right triangle, z and x, script r is square root of x squared plus z squared. I just wanted to show another way that you could obtain that answer, and it's up to you how you want to get it. Then your potential is going to be 1 over 4 pi epsilon naught. We're going to integrate from negative L to L. So that line of charge has a length 2L, and if it's got perfect symmetry, which it looks like it does, this part is negative L, and this part is L. So that's our bounds of integration. And then we'll have lambda over x squared plus c squared dx. Now, I'm not going to go through and solve this integral. It would be a trig substitution, it looks like, unless you know another way to do it, but that's what I would do. But again, this class isn't really designed to test how well you can apply your methods of integration. That's a Calc 2 class. So we're good there. So I'm just going to use an integration table. And I am perfectly fine with that. This will likely be given. And that is what the integral ends up giving you. So that's your potential. And if you wanted to, if you took the gradient, basically you take the partial with respect to z in this case, the negative gradient that is, you could find your E field. Again, I'm not going to do it because it's just essentially taking a derivative. I'm trying to manage my time. For part C, so now we don't have line charge density, we have an area charge density sigma. And let's just call this, that's your script r. We'll say it's some distance little r. Big R would be if you're at the actual end of the circle, and we don't know if you're going to be there or not, so we'll just call it little r. So for C, the potential is 1 over 4 pi epsilon naught. The integral, again we'll call it a b, dq over script r. And dq is going to be sigma times dA. So sigma is charge per area, and we're multiplying it by an area element, so you get your charge. Script r, again, is just going to be z squared plus little r squared. So this time I just looked at it and said, well, instead of breaking it down systematically, you could have done it, you could have done that as well, but it doesn't matter. You could have done it like we did in B, where you define your r vector and r prime vector, subtract them. Could have done that, but you can also look at it and see that script r is what it is. As for dA, well, the area of a circle is pi r squared. So if we do differentiate both sides, you'll get 2 pi r times dr, because we have to do it implicitly. So that's your dA. Maybe I should have called this little a to be consistent. dA. So this will be plugging into our dA here. So then our potential is 1 over 4 pi epsilon naught. If you think about our bounds of integration, we want to go from this center all the way out to the surface there at r. So our bounds of integration will go from 0 to big R. We said dq is sigma times 2 pi r dA, or dr, I'll put that up there. This is our script r times dr. So you can pull out your constants here, and v is equal to 1 over 4 pi epsilon naught times 2 pi sigma square, or the integral from 0 to r over z squared plus r squared square root dr. This one's not as bad to solve. I'm going to skip the integration, but now it's actually a u sub. So you can let u equal z squared plus r squared, and 1/2 du is equal to r dr. So I'm going to skip the integration part and just give you what you get when you actually work the integral out. And you get v is equal to 1 over 4 pi epsilon naught times 2 pi sigma over the square root of z squared plus r squared minus c. It's just a u sub, so it's nothing crazy. This is your u. This is 1/2 du. And then you're essentially going to be integrating this, which is just a power rule, so nothing crazy. And again, I'm not going to take the derivative, but if you took the derivative of this with respect to r, or I'm sorry, z, which actually isn't too bad, then you'll get your E field. But yeah, that's how you find the potential for